So hello students, almost we have covered the last theme of this topic, that is molecular orbital theory. Okay, the important point was we have to remember the energetic order of different molecular orbitals, and two different orders were given. One order was applicable up to 14 electron species, that means up to nitrogen molecule you can say, and above 14 electron species the configuration, molecular configuration was different. Okay, so the main point we have to remember these two orders. In the last class I have given you people a task about N2 molecule, N2 plus, N2 minus and N2 2 minus. Write down the molecular configuration of all these ionic species including dinitrogen molecule. Calculate the bond order of different species and finally their magnetic character and stability. Okay, so since we have covered the fundamental things behind all these topic, let's discuss about N2. Okay, N2 molecule, probably it's easy, I have told you. Dinitrogen, that is N2. So how many electrons have to distributed in different molecular orbitals? That is, for two nitrogen atom, each having 7 electrons, so 7 plus 7, that is 14 electrons has to be distributed in different molecular orbitals. So the molecular order of a molecular configuration, the molecular configuration can be given as sigma 1s, sigma star 1s, sigma 2s, next that is sigma star 2s, next pi to px, that is equal to pi to py, that is sigma to pz, next one pi star to px, pi star to py, and finally that is sigma star to pz. Okay, so if you mention the electrons, 14 electron species like 2 electron over here, 2, so totally how many electrons? 2 to 4 to 6 to 8 to 10 to 12, and here is 2 electrons, 12 to 14. So this includes the molecular configuration for dinitrogen. So now we just calculate its bond order, that is half into number of bonding electron minus number of anti-bonding electron, half into number of bonding electron without star mark. You just see 2 to 4 to 6 to 8 to 10 minus anti-bonding electrons you can calculate 2 to 4, okay, it's 4, so that is 1 by 2 into 6, so bond order is 3 in case of a N2. Next, for N2 plus, that means you have removed 1 electron, that means it includes 13 electrons, and that electron can be removed from the higher energy molecular orbital, that is from sigma to pz, so here will be 1. Okay, so the configuration, if you write down its molecular configuration, then that sigma to pz will be 1. So directly I am writing over here bond order. So the configuration of N2 can be followed like this: sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi to px2, pi to py2, and here sigma to pz1, one electron being removed. So here you can calculate bond order, that will be half into Nb minus Na. So half into number of bonding electron will be 9 in this case, 9 because one electron from here get lost. So 9 minus number of antibonding remains same 4. So that will be 1 by 2 into 5. So that will be 2.5, 2 half. Okay. Next, if I consider N2 minus, see over here, one electron being added and that electron will be enter into this antibonding because all are filled by electrons. So the extra electron get added to this antibonding orbital pi star to px, or you may add over here pi star to pi because energetically they are same, degenerate orbitals. Okay, so it's very easy. If I place one electron over here, then number of antibonding electrons becomes more, 1 over here. So you just calculate the configuration here for N2 minus, the molecular configuration can be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Okay, then that is pi to px2, that is equal to pi to py2, that is equal to, okay, less than sigma to pz2, and here pi to px, that is equal to pi to py, antibonding orbitals here will be 1, this much. Okay, so you calculate now bond order, that will be half into Nb minus Na, half into Nb, definitely it will be 10 minus, but here antibonding becomes 5, one more electron is there, so it will be 5. So that is 1 by 2 into 5, again it is 2 half. Okay, the next one, that is N2 2 minus. So now the next electron enter into this 2py because these are energetically same. According to Horn's rule, degenerate orbitals will be filled single first, then pairing starts. So you have to supply one electron over here, again here. Okay, so next again configuration sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Next, that is pi to px2, that is equal to pi to py2, less than sigma to pz2. Okay, next pi star to px1, that is equal to pi star to py1, this much. Okay, one more antibonding electron is there. So here if you calculate bond order for this one, half into Nb minus Na, that is equal to half into Nb, number of bonding electron, that will be no doubt 10, but antibonding electron becomes 6 over here. So that is half into 4, so the bond order will be 2 over here. Okay, so if you compare the bond order, highest bond order you have got for N2. So regarding the stability, order of stability, bond order of N2, N2 plus, N2 minus, N2 2 minus. For N2 you have got 3, for N2 plus you have got 2 half, for N2 minus again you have got 2 half, and for N2 2 minus you have got 2. Okay, so regarding stability I have told you, more the bond order, stability will be more. So here the stability, maximum stability will be N2. So the stability order will be N2 more stable than N2 plus, that will be equal to N2 minus, and the final, that is N2 2 minus. Okay, so this one will be the stability order. But one fundamental thing over here is, if you compare this N2 plus with N2 minus, you see have same bond order. Okay, but practically this N2 minus becomes less stable than that of N2 plus. Why? Because of one extra electron over here, the bond pair electrons are negatively charged and this negative charge repel to one another. Okay, this extra electron having negative charge and the bonded electron also having negative charge, so negative repulsion is there, so this N2 minus becomes less stable than compared to N2 plus, but fact that is very negligible and the order follows this order: N2 more stable than N2 plus is equal to N2 minus, and finally that is N2 2 minus. That clear? It's very easy. Okay. Next, another thing is about their magnetic character. Magnetic character means, I have told you, if there is presence of any unpaired electron, then it is paramagnetic. If all the electrons are paired, then it is diamagnetic in nature. So for first one, N2, you see there is no unpaired electron in case of N2. Okay, so up to sigma 2pz2, this one also 14 electron space, you see all the electrons are paired. Okay, so N2 is diamagnetic. Here this N2, this is diamagnetic, no unpaired electron, diamagnetic. Next, N2 plus configuration having one unpaired electron at sigma z, so it is paramagnetic in nature. Paramagnetic. Again, in N2 minus also there is one unpaired electron at this anti-bonding orbital, molecular orbital, so this is also paramagnetic. And N2 2 minus, there are two unpaired electrons, so this is highly paramagnetic, because paramagnetic behavior depends upon number of unpaired electron. There is two unpaired electron, so this is also paramagnetic in nature. Paramagnetic in nature. Okay, so this is about their paramagnetic nature. Again, since you know the noble gas elements do not combine with one another, like that of He2 molecule never exists. At the beginning I have told you, whenever two helium atoms approaches to each other, then what happens? The number of repulsive force predominates over the attractive force. Therefore, the formation of a helium molecule is not possible. Let us explain how this helium molecule is not formed on the basis of this molecular orbital theory. Okay, so I can write over here He2 is not formed. I have to explain it through molecular orbital theory. So in He2, how many electrons total? He2, so total that is 2 plus 2, that is 4 electrons. Okay, so 4 electrons can be arranged like sigma 1s, sigma star 1s, but this much 2, 2. You see, if you calculate over bond order, half into Nb minus Na, so half into number of bonding electrons 2 minus number of anti-bonding also 2, so half into 0, that is bond order is 0. That means there is no bond between helium atom. If you consider neon, so how many electrons? 10 plus 10, that is 20 electron species. So the order will be the second one, that is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, and next one that is sigma to pz, next pi to px, that is equal to pi to py, pi star to px, that is pi star to py, the final that is sigma star to pz. So this is the order. So how can you arrange these 20 electrons? 2, 2, 2, 2, 2, 2, 2. So how many electrons you just calculate? 4, 8, 12, 14, 15, 16, 17, 18, 19, 20. With the order. So if you calculate bond order, half into Nb minus Na, half into Nb, number of bonding electron you calculate, 2 to 4 to 6, 10, So 10 number of bonding electrons minus number of anti-bonding 2 to 4 to 6 to 8 to 10. You see, again the bond order becomes 0. That means there is no bond exists among the noble gas atoms. That's why they do not form any molecule. Okay, because their bond order found to be 0. There is no bond between these atoms. Clear? Now let us discuss, although it's beyond your syllabus but very interesting, for heterodiatomic molecules, how the molecular orbital theory suggests for heterodiatomic molecules or heterodiatomic molecular ions. So let us discuss about CO and CO plus. Okay, so in CO total electrons to be distributed, that is for carbon you can take 6 plus 8 14 electrons. That clear? So for 14 electrons the electronic configuration can be written as sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, next that is pi to px, pi to py, next that is sigma to pz, pi star to px, pi star to py, sigma star to pz. This is the order. So 14 electrons, it's just like that of nitrogen. You have to arrange like this: 2 2 2 2 2 2 2. I think you just calculate 2 to 4 to 6 to 8 to 10 12 13 14. Okay, need to calculate its bond order, that is half into Nb minus Na. So Nb, that will be 10 2 to 4 to 6 to 8 to 10 minus antibonding 2 to 4. So half into that will be 6. So the order is 3. Okay, for CO plus beta, CO plus, loss of one electron, that electron can be removed from here, higher energy orbital. So this sigma to pz becomes 1. So I am directly writing over here half into number of bonding electron becomes 9. To removal of one electron 9 minus antibonding remains same 4. So half into 5. So that will be 2 half. This is the bond order. So more the bond order, less will be bond length, because you know bond order is inversely proportional to bond length. Am I right? So by considering this relationship, the bond length of CO plus is less than, the bond order of CO, the bond order of CO is more than that of bond order of CO plus. So conversely I can conclusion, that is bond length of CO becomes less than that of bond length of CO plus. But practically the case is reverse. That means the bond length of CO plus is more than that of bond length of CO. Okay, so this is happening. The reason behind it is what? The 2s orbital of carbon atom, the 2s orbital of carbon atom, the 2s orbital of carbon atom has higher energy than 2s orbital of oxygen atom. That means the reason is this 2s orbital. this 2s orbital of oxygen atom is lesser in energy than the 2s orbital of carbon atom. So what happens, this 2s and 2s combines to form bonding molecular orbital, that is sigma 2s, and anti-bonding molecular orbital, that is sigma star 2s. Okay, so due to the lesser energy of a 2s orbital of oxygen atom than that of a carbon atom, so whenever they combine to one another to form molecular and anti-bonding molecular orbital, this sigma 2s becomes stable, and this anti-bonding molecular orbital sigma star 2s becomes highly unstable. Suddenly its energy becomes enough so that it will shifted to here, shifted to up to here. Okay, so even after this pi to px and pi to py, so the configuration is changed. Like, let me write down it's a configuration. So the configuration becomes, okay, let me, so due to this reason, the sigma star 2s anti-bonding sigma star 2s becomes highly energetic, even it can overcross your sigma to pz, it really comes to here. So the advanced configuration can be sigma 1s2, sigma star 1s2, sigma 2s2, next pi to px2, pi to py2, sigma to pz2, and finally the highest energy having sigma star 2s2. So this is the new configuration and possible configuration for CO. Right now you can calculate its bond order. This one is the molecular configuration of CO, proper molecular configuration. Okay, so if you calculate the bond order in this case, that will be half into number of bonding electron. You can calculate right now 2 to 4 to 6 to 8 to 10. 10 minus number of anti-bonding, calculate 2 to 4. So that will be half into 6, 3. It will be 3 will be bond order. And for Cu plus, right now this is the basic configuration. For Cu plus 1 electron can be removed from here. So number of anti-bonding electron becomes less 1 electron. That is bond order. Now you can calculate half into 10 minus anti-bonding becomes 3. So that will be 1 by 2 into 7. So 7 means that will be 3 half. Now you see the bond order of Cu plus becomes more than that of bond order of CO. So regarding bond length, you can say bond length of CO becomes, bond order of CO plus is greater than that of bond order of CO. So bond length of CO plus is less than that of bond length of CO. You see, now the case being reversed. Practically bond length of CO plus is less than that of bond length of CO. Okay, so what we have suggested over here, so now you see the case is reversed. If you consider, but practically the order becomes 3 and 3 half. So now the bond length of CO plus becomes less than that of bond length of CO, bond length of CO plus less than that of bond length of CO. So this is the practically proof of this deviation. Okay, so students, in next class we will discuss few application or few questions in the chapter chemical bonding. But till now this much. Hopefully you get it well. Okay, so thank you.